Alright, in the previous video, we've discussed the Eulerian and Lagrangian descriptions of fluid flows. And we introduced the concepts of streaklines, pathlines, and streamlines. In this video, we're going to explore how to express streamlines and pathlines mathematically. Okay, that is, we know that a streamline is everywhere tangent to the local velocity vector. So given a velocity field, can we find the equations for these streamlines? So this will give us a geometric representation of the flow. It'll give us a sense of what the flow is looking like. So let's consider here, we have a streamline in red, and as per its definition, it is tangent to the local velocity vector v. Okay, so perhaps my drawing is not the best, but we have a velocity vector v over here. We have a streamline over here. Now recall that our velocity vector v can be decomposed into its x and y components, u and v, respectively. And by definition, we can look at the tangent as, we know that the tangent will be described by a certain slope. So we can look at dy and dx at, let's say, a certain point P over here. Okay, so dy and dx are the, rise over run locally at point P of the streamline, which we hope to be able to define mathematically, functionally, perhaps something like y as a function of x. Okay? So we see here that we have similar triangles, so we could say that dy by dx will be equal to v over u. That is, the local slope of the streamline is equal to the ratio of the vertical and horizontal velocity components, v and u. And that is it. This is precisely what we're going to use in order to find a functional representation, let's say y is equal to a function of x, for our streamlines. So let's consider a velocity field over here. So it is given by the negative of v naught y divided by x squared plus y squared and the square root thereof, plus v naught x divided by the square root of x squared plus y squared. So as you can see, this over here is your u component, and this over here is your v component. And v naught is some constant. Okay? So as we can see, this velocity field is steady. It is not a function of time. The time variable does not appear. But it is a function of x and y. So here what we're going to do, we're going to try to find where in the flow the magnitude of the velocity vector is equal to this v naught constant. And also we're going to look to find the equation for a streamline. All right, so recall that the magnitude of the velocity vector, or the speed, if you will, is equal to u squared plus v squared. I'm going to clean the square root over here a bit. All right, that's slightly better. All right. So looking at our u and v components, u squared will be v naught squared y squared divided by x squared plus y squared plus v naught squared x squared divided by x squared plus y squared. And all of this is raised to the power of 1 over 2. So let's group like terms. We see we have the same denominator everywhere, so we can just add up the numerators there. We're going to factor out v naught squared, so we have x squared plus y squared, and then we're dividing by x squared plus y squared, and we're taking the square root of this whole thing. Now, as we can see, x squared plus y squared cancel out, and so we find that, in fact, the magnitude of the velocity is v naught everywhere in the flow. So what we could say is that the speed of the flow is v naught everywhere. And this is only for this particular velocity field representation. So let's now describe what the flow looks like. So for a streamline, we have said that the slope of the streamline, dy by dx, will be equal to v over u. So we look at our v component, we look at our u component, and we divide them. So we have v naught x divided by x squared plus y squared to the 1/2, and all of this divided by negative v naught y divided by x squared plus y squared to the 1/2. So we see v naught and v naught cancel. Also, our denominators cancel out. So we are left with the negative of x over y. So let's spread this out over here. We have dy by dx is equal to negative x over y. So, if you thought that you could escape your study of differential equations, I'm sorry to disappoint. This is a differential equation, but luckily it's as straightforward as they come. This is a first order separable differential equation. Okay? So we can separate out the terms. So we have 1 over x dx is equal to the negative of 1 over, oops, sorry, I made a mistake here. We have 1 over y dy, oh, I'm still making mistakes here. Y dy is equal to the negative of x dx. And so we can go ahead and integrate. We have an indefinite integral here. And so we find that we have y squared over 2 is equal to the negative of x squared over 2 plus an integration constant c. Now we can absorb these 1/2 into the integration constant, which will give us x squared plus y squared is equal to c. So what does this tell us? This is the equation for a streamline for our velocity field given here on the left. So the streamline is everywhere tangent to the velocity vector. and it is defined as x squared plus y squared is equal to some integration constant. And what these are actually just circles. So we have one streamline over here, which will be associated with a certain integration constant. We'll have another streamline over here, another streamline like this. And again, everywhere tangent to the local velocity vectors. Okay, where the magnitude of the velocity vector is equal to v naught everywhere. So over here as well, the magnitude is equal to v naught. So this velocity field over here, described by this seemingly complex vector equation, is in fact a fairly simple flow where the streamlines define concentric circles where the speed is v naught throughout. So here you have seen how to describe mathematically the equation for a streamline based on this very simple relationship between the local slope and the velocity vector components. Okay, now we move on to describing path lines. So consider this velocity field over here. We see that it is time dependent. Okay. And now the path line is the path traced out by a single particle. Okay. So it is the curve traced by a particle as we follow it through space and time. Okay. So what we can do here to find the path line is to consider the x and y components separately. So we have, for example, the x component of velocity, which we define as u. And you can imagine that the x component of velocity is the time rate of change of dx by dt. So u, our u component over here, is the time rate of change of the displacement in the x direction. And v, which is the time rate of change of the displacement in the y direction, and that is just equal to 2. Okay? So what we want to try to find is something in the form of x of t and y of t. You know, how does the particle evolve through time in space? Okay, so what will be the position of a certain particle, x or y, as a function of time? So if we look at the x component first, right? So we have dx by dt is equal to x divided by 1 plus t. And again, this is a fairly straightforward differential equation. It's first order. It's separable. So let's separate our variables. We have 1 over x dx is equal to 1 over 1 plus t dt. And we can integrate this. And just to kind of change things up a bit from how we did the streamlines, here we'll do a definite integral, you know, between some point x naught and an arbitrary point x, and some point t naught and an arbitrary point t. So if you recall the description or the definition of a path line, it is passing through a certain point at time t naught. And that certain point is given by x naught. In the y direction, it will be y naught. Okay, so we integrate, so we find we have here ln of x minus ln of x naught is equal to the ln of 1 plus t minus the ln of 1 plus t naught. Okay, recall your laws for logarithms. You can combine this as x over x naught, and this will be equal to the ln of 1 plus t over 1 plus t naught. And this will just help us to isolate x of t. Okay, so if we take the exponential of both sides, we recover what's inside the brackets. So we're just going to have x over x naught is equal to 1 plus t over 1 plus t naught, or x of t is equal to x naught multiplied by 1 plus t over 1 plus t naught. So this is how the position in the x direction of a certain particle which has passed through x naught evolves through time. So the position x is equal to the initial position x naught multiplied by 1 plus t, where t evolves through time, divided by 1 plus t naught. If we look at the y component, right, so we have dy by dt is equal to 2, or we could say that, okay, I guess I'll go through the whole thing. So we have dy is equal to 2 dt, which again, we can integrate from y naught to y and t naught to t. So in this case, we're going to have y minus y naught is equal to 2 t minus t naught, or y of t is equal to y naught plus 2 t minus t naught. Okay, so we found x of t and y of t. We could stop here if we wanted to, but the path traced by this particle is not really apparent from our expressions for x of t and y of t. You know, what is this path that, you know, we have a particle that passed through x naught, y naught at a time t naught. What does that path look like? What does the line that is traced out by this particle look like? We can make these expressions more geometrically useful by eliminating t from both parametric expressions. Okay, so let's isolate t in our expression for y of t. So we find that t is equal to y minus y naught over 2 plus t naught. Okay, so we can express t as a function of y. And then what we're going to do, we're going to substitute this expression for t into t, which appears in our x of t. So we're going to have x of t is equal to x naught over 1 plus t naught multiplied by 1 plus t, where we have 1 plus t from y of t, which is y minus y naught divided by 2 plus t naught. Okay, and with some manipulation, because hopefully, you know, we know how to plot things generally when they're kind of, you know, y is equal to f of x, something like that. So we're going to isolate y with a little bit of manipulation. So we find that y is equal to 2x 1 plus t naught divided by x naught plus y naught minus 2 t naught. So this is the path traced out by a particle which has passed through x naught, y naught. And as we can see, this is much more geometrically useful than our parametric expressions for y of t and x of t. And the reason being that, it is not very clear to us what what this path looks like. But once we put it into a form that is familiar to us, we see that we can actually see that this is just the path described by a straight line, right? So t naught is a constant, 1 is a constant, x naught is a constant, and 2 is a constant. And this entire bracketed term here is a constant as well. So this is just in your very familiar high school form of y is equal to mx plus b. So what we find is that the vector field described over here, which is time dependent, has a path line described by a straight line defined by this functional relationship over here. So in this video, you have seen how to calculate streamlines and pathlines given a certain vector field representation. In the coming videos, we're going to look at applying Newton's second law along a streamline. And what we're going to find is that it gives us the very well-known Bernoulli's equation.